Good morning, welcome to Krishna's class. In the last lecture, we concluded the proof of the Rees representation. And in fact, we showed that from linear functionals, you can go over to measures and consequently to a measure space and integration. This was the outcome of that theorem. Now, what we are going to do in this lecture is to explore how this idea can be made use of to introduce Lebesgue measure on RK and Lebesgue integration theory and subsequently developing the Lebesgue integration theory. Now recall, we did it for R1. In the case of R1, we started off with the Riemann integral. Then we found that there are some inadequacies for that. And then we wanted to rectify that. This is how we arrive at the Lebesgue integration theory. And then we found that you need the concept of length for a larger class of subsets of R than intervals. And our effort was to develop this. I have already discussed all these things in detail and you can just refer back. And we successfully did that, and for a wide variety of class of subsets, we could introduce the concept of length, which we call the measure. This was called the Lebesgue measure. And then consequently, integration theory was developed. Now we want to do the same thing, but we are not going through the same track. What we are going to do is make use of the Rees representation theorem. That means we start with a suitable non-negative linear functional on CCRK. We will work with take CCRK, start with a non-negative linear functional. Linear functional on that, and then through that we introduce a measurable class of functions and on RK. So we introduce the measure space, and this turns out to be the Lebesgue measure on RK, because everything hangs on the choice of this one. How we do that? Because you know that the Lebesgue measure has certain nice properties, namely, if some subset is measurable, then every translate of that is also measurable, and the measure of the measurable set and its translate are same. Okay, that is, the measure is invariant under translation. Now this is one of the crucial properties of Lebesgue measure. It's a very important property. That's a desirable property that we would like to have. Therefore, one has to be careful in picking up lambda, because the representation theorem is very general one. It doesn't talk about translation or any such thing, because you may not have such structures on X to start with, but on RK you have is rich with linear space structures, and also the topology induced by the metric, etc. So, all these advantages are there on RK, and we would like to pick the right kind of non-negative linear functional on CCRK, okay, which generates the Lebesgue measure and the Lebesgue measurable sets and Lebesgue measure, so that we can naturally extend the integration theory from R to, or generalize the integration theory from R to RK, okay, analogous to what we had in the Lebesgue measure. Now this is the whole thing that we are planning. So with this objective, we start with looking at the structure of RK. This we already know. But still, it is better to fix the notation before we start with the development of the theory. So let us make some definitions and notations which are crucial or which are required for our purpose. So this is the N tuple or K tube. We are working with RK. Psi I now this is what RK is. It is actually R cross R cross R cross etc. on which an R, when it becomes RK, you have additional structures on that. We have not said anything about the structure, but we will do it. Now for X, Y belonging to RK with X defined as psi K and Y defined as eta 1, eta K, where psi 1, psi 2, psi K and eta 1, eta 2, eta K are all real numbers. These are some two arbitrary elements of RK. Define X plus Y to be the N tuple obtained by adding these two vectors component wise. So what you have is psi K plus eta. Also, scalar multiplication we define. Alpha x is defined as, where alpha is a scalar, where for every alpha belonging to R. So these are the, or this is the rule of addition and this is the rule of scalar multiplication, which is generalized from what we our experience on working on vectors in R2 and R3. And in R2 and R3, the vector addition is not something that something that was mathematically crafted, but it came from nature. Well, you can look into the earlier part of my lectures on linear algebra. Okay. So then with this addition and scalar multiplication, Rk is a k-dimensional vector space over R. It is a very heavily loaded statement. First of all, it's a vector space. That means all the properties of the vector space are satisfied by Rk, and you have a statement of a k-dimensional. That means a carefully chosen k vectors which are linearly independent in Rk would generate the whole of Rk through addition and scalar multiplication. Okay, or we shall call this, since this R is the associated field, and we also call this a real vector. That is because analogously you can talk about Ck over C. That's also a k-dimensional vector space where C is the complex field. Okay, and now you see that this is Rk, which is a generalization of R2 and R3, which we are familiar with. So the guideline for what properties are to be there is coming from our experience of working with R2 and okay. Now we have the concept of dot product on R3 or R2, and analogously you have the dot product or what you call inner product you see, this is the algebraic structure. The linear space structure is the algebraic structure. The dot product or inner product on Rk is defined by x dot y theta I for x, y belonging to now this is what it is. So that's about the dot product or what you call the scalar product or what you call the inner product. All these are the various terminologies that you have. And from this we can define the length of the vector. This is defined as x dot y, sorry, x dot x to the power. So this defines the length of x. Now, one of the interesting features of this inner product or dot product is that it satisfies the Schwarz inequality. It's called the Cauchy-Schwarz inequality. Schwarz inequality. What you have is this. This is a scalar. X dot y is a scalar, and its absolute value is given here because it's a scalar, and this is less than or equal to incidentally this and this bars have different meaning. Now this is just the absolute value. This is actually the norm, okay, or norm or length. Now this is also called norm. So this is absolute value because it's a scalar, and this is what you call, so that has to be taken, although we use the same notation, and I think it should be clear. Now one can have, see, so from RK, take an X belonging to that, associate with it mod X belonging to R. So we can show that this is the following property, namely this is what is called the norm. Norm satisfies the following property, namely norm of X greater than or equal to 0, norm of X equal to 0 when only if X equal to 0. By this is the 0 vector, and this means X equal to 0 means all the components I1, I2, etc. I are 0. That is, that's that. And then you have norm of alpha X equal to mod alpha norm X. See, once again, this is a scalar, this is the modulus of that, this is the length. Okay, so this is a vector, so this is norm, this is absolute value, this is again norm. Satisfies this condition, and further norm of X plus Y, norm X plus norm for every So this is what is called the essential properties of what is called the length function. Okay, so it satisfies all the properties of the length function, and therefore RK is norm linear space. Now the norm induces a length, a distance. Distance. The distance. And this is defined by d of xy and once again you can prove that dxy 0 is dxy equal to 0 and only x equal to 0 dxy equal to d by x. This is symmetry. It simply says that the distance from x to y is the same as the distance from y to x. And finally, dxy is less than or equal to d yz dxz plus d for every that means all the basic properties required for a length function are satisfied by or for a distance function are satisfied by dxy. So dxy is essentially concept of a distance from x to y. What does that do? So rk with d is then matrix. And the metric is given by what does it mean? Every metric space is a topological space. It's a topological space. The open sets defined by determined by the metric so what you have now, we have two things now. One, rk is hence rk is a linear space over R. This is what we call an algebraic space. This is the algebraic structure. Now it is also a topological space. Rk is a topological space, and this is what is called the topological space. So two structures are there. One is the linear space structure. The other one is the topological structure. Okay. Now, when you have two structures sitting on the same space, you cannot have something creative happening unless they interact positively. Positively means smoothly. Unless they are smoothly interactive, nothing would come out of it. There will be all sorts of problems for further. But fortunately, here these two structures smoothly integrate. So these structures smoothly interact. This is assured by the fact that the vector space operations continuous with respect to the topology. What do you mean by that? That is, Xn converges to X implies X plus Y and alpha n converging to alpha further alpha n converging to alpha and xn converges to x implies alpha n xn, the sequence alpha n xn converges to alpha. That means, see, structurally what is happening is that, see, you have a topology on Rk. Now, you know that addition is a map from Rk cross Rk to Rk. What we assert is that, see, Rk has a topology, therefore you have the product topology on Rk cross Rk. So this is a topological space. This is already a topological space. Addition is a map from one topological space into another topological space, and it is sensible to ask the question whether it is a continuous map or not. What turns out is that is continuous. Similarly, the multiplication is a map from R cross RK. Is continuous. That is the meaning of that. Okay. That means addition is you take an ordered pair xy from RK cross RK and apply the map of addition. You will get a vector in RK as x plus 1. Okay. What we are saying is that this map, second continuous map, similarly, you take an alpha from R and an x from RK. So you have, see, two things, x, y, that is the addition map. Then this is alpha x getting mapped to, this is the multiplication map. Okay. So these two maps are continuous maps, and it is quite is well supported by whatever we have defined. And in turn, this is established by proving if xn is a sequence which converges to x, yn is a sequence of vectors which converges to y, xn plus yn is a sequence obtained by adding them, and that converges to x plus y. Similarly, alpha n converges to alpha, xn converges to x, plus that is, this is the conceptually what is happening. Okay. So the two structures that lie on RK gel together, and that's the important part. Okay. Now we introduce, this is just a recall of some of the basics on RK. Now what we want to do is we want to work on we want to introduce the concept of measure, etc. So as a, okay, what is a basic property of the Lebesgue measure on R? It is translation invariant. That means if E is a measurable set and E plus X is its translate, then you see that the measure of E equal to measure of E plus X. This is the property. So we prepare the ground for that. So on RK, we define the translate. So definition, we find the translate of E by X belonging to RK or rather through take all the elements Y belonging to E and then add to them X. You get a new set of points in R. Okay, and that collection is what is called the translate of E to the vector. Geometrically, if you recall in R2, geometrically this is, suppose this is your E and then this is the vector X. then what you are doing is you are pulling this set in distance, keep the same shape. Okay. So you have all these elements moving to. Okay, so this is equation. So you literally shift the subset through the vector E and you get a new subset, and this is what you call equations. Okay. Now we make a new definition. So that is clear. See, for everything R2 or R3 is the model, is the that because there you have perfect visualization of what is happening, and that has been mathematically said about for any case. Now we define what is called, this is the translate. Case. You define W to be the set of all X. X has components psi1, psi2, etc. Psi k, I don't want to repeat it over and over again. Where alpha I less than psi I less than beta. Where alpha I are beta I for I equal to this is what I have. Okay. And this is in fact what you have is this. This is in fact the interval alpha I beta I, or the set where these are intervals. These are all intervals. Okay. So you take the open interval alpha I, beta I. For each I, take the product of this. This collection of points is what is called W. Okay. So that's about the openness, but we shall also use the same W. Okay. Or not completed the definition. This is it. Or obtained by replacing the sine with less than or equal to at some places or all places. Now I'll just explain what I mean by this. What I mean by this, let us look at in R2. Take R2. So you are talking about W to be X, which is equal to X that. You have got alpha 1, beta 1 and alpha beta 2, where alpha 1, alpha 2, beta 1, beta 2 are real numbers with alpha 1 less than beta 1, alpha 2 less than beta 2. So this is geometrically, see, this is actually R4, R2. So you have alpha 1, beta 1 right. This need not be in the first quadrant, can be anywhere. I'm just giving a feeling for what it is. See, what we end up with is a rectangle. In fact, since the boundary is excluded, because we are taking this one, then of course we are only talking about the interior. But suppose, see, what are the possibilities that you have? Here there are 4 possibilities. W can be 1, alpha 1, beta 1, interval alpha 2. This is one possibility. W could be second possibility is next. The third possibility is there are 8. Not 8, much more than that. So 4 different ways in which you can have this interval, and this keeping this as an open interval. Now, you see, there are how many different choices are here? There are 4 different choices. So what you have? So you have 4 into 4. So it is, there are 16 types of W. Okay, 16 types of W that you can have with this choice. Okay. Now for each of this, now you can change this, and then again all the four possibilities are there. You can change this, and there are another four possibilities. And then suppose you take include alpha 2 and beta 2, then there are four different possibilities. So there are altogether 16 different type of W's that you can craft from these numbers alpha 1, beta 1, alpha 2, beta. Okay. So for instance, the second one that you have considered, it will be the, see, alpha, this line will be included, this open line will be included, but with the same, all other points remaining same. In the third one, it is going to be this line. Sorry. Okay. What I mean to say is that in the first case it is going to be the interior of this. The second case, it is going to be this line included, but not the end. Then the third case, it is this line is included and the interior of this. So these other lines are not included. In the fourth case, what happens is both these are included. Okay, and likewise in all different cases. 16. Okay. Right. Now, that is in R2. When you work in R2, there are several possibilities that you can actually combinatorially easily work out the number of such W's that you can. Anyway, that is irrelevant. What is the area enclosed by this rectangle? It is the length of this multiplied by this length of this. Whether the boundary is included or parts of the boundary is included or not, it is the same. Therefore, in all these cases, you have volume of W to be equal to beta 1 minus alpha 1 into alpha. Okay. So, in general, what is the volume? So, volume is actually not, see, it's a hypervolume actually. Okay. But we designate volume of W. No matter whether the boundary is included or the parts of the boundary is included. Now this is the volume. This is something that we will see in our analysis. Okay, right. Now, what is our strategy? So our strategy, now you know that how to find the length of or the measure of a set. This we have analyzed earlier. So here, let us look at the possibility of a nice set in R2. How do we find, suppose there is an irregular region and you want to find the measure of. So what you do is, you use the graphing techniques, graph techniques. What you do is, you have got, suppose these are unit distances that you have. Similarly, you have unit distance. Now, what one observes is that there are certain squares which gets fully trapped inside this, and you can count actually the area of the fully trapped squares of unit distance. Now, what one does is you subdivide these intervals further into 1 by 2, the middle, or actually, into two equal parts, each of this interval, and then draw the graph. Now, what happens is, apart from this, the area covered by these rectangles that you would have some more area taken care of by rectangles of the type. See, what you have is this. This is that of unit length. You are dividing this, so you divide each of these rectangles by into each the sides of these rectangle. This unit length into 0 to half and half to 1 and so on, and then of length of half the unit length, then there are 4 such squares. So you can see that, for instance, this is something where it is not fully a square, does not, but what happens is you divide this. Now you see that this square goes. See, it allows you to reckon the area beyond what you have already added. Okay, all others are cut. Therefore, what you do? Further divide. Okay. Then what happens? Smaller squares will come, and this is the process of actually finding the area of an irregular, space in R. Right? So we employ this particular technique, and with this objective, we introduce the right kind of notation for that, and then work out the possibilities, and then try to express what are called open sets in RK in terms of find the areas enclosed or volume enclosed by open sets in RK in terms of these kind of areas of these kind of cubes. Okay, so that will be our topic for discussion in our next lecture, which I hope I will do. Okay, and then prove a crucial result which enables you to find the find the area of some subsets in RK. So thank you very much, and we conclude today's lecture here, and we continue tomorrow.